Optimization, the final boss of calculus. You've battled through derivatives, you've conquered stationary points, and now you're up against these confusing, wordy, big multi-step problems in optimization. If you have been struggling with this difficult topic, look no further. I am here to rescue you. Today, I'll show you how to break down these tricky optimization problems step by step, and by the end of it, you might actually find them pretty predictable. Hi everyone, and if you're new here, welcome. I'm Jessie, and these are my notes. I break down maths in a way that actually makes sense, and I give study and productivity tips to help you navigate high school. If you're ready to enter your study era, hit that subscribe button and let's get back to the video. So to start off this topic, I'm going to break down what the word optimization means. When you see optimize, it's kind of like optimal. It means it's the best. It's the best possible case. And what we're optimizing are all sorts of different quantities. You could optimize the area. You could optimize the volume, the cost, the time, the distance, the speed, everything, any sort of quantity. So this is going to be where you really challenge your understanding on a wide variety of different topics in maths. So let me give you a little bit of an analogy to explain when someone might be using optimization to help them solve problems. So let's say you're in the business of manufacturing these boxes. Yes, just the boxes. And you want to be able to hold certain products that people want to sell. But you have to remember that if you want to maximize your profits, you need to use as little material as possible while still being efficient, or while still being sufficient. So what you might do here is you might want to find out the different dimensions. So what is the length, width, and the height of this box, such that you have the minimum surface area, which will then in turn allow you to maximize your profits. So you can see that there are many different ways that you can optimize. Another way you could optimize is, let's say you have a bunch of workers and you know that they need a certain amount of time to produce these boxes. If you were to try to maximize your profit, you may want to minimize the amount of time that your workers are out here actually doing their work. So here I have a step-by-step guide that you can follow to help you answer any optimization problem. So the first part is you want to identify the quantity that needs to be either minimized or maximized. So that's what it means to optimize. You either want to find the minimum of something, like the minimum surface area, or you want to find the maximum of something, like the maximum profit. And you could have all sorts of different quantities involved. This next step is to create the function you need to optimize in terms of one variable. This is a very important step, and this is arguably the most challenging step in any optimization problem. So over here, this is an example of having your quantity, which looks like its area, in terms of one variable, which is x. It doesn't have to be x, it can be p, so it can be like a is equal to p squared minus 2p, but the idea is it's only in terms of one variable. If you look at this one over here, you can see it has two variables, which is incorrect. So you need to manipulate it, or you need to use other info provided in the question to force it to look from looking like this to look like this. Step 3, find y dash and let y dash equal to 0 to find your stationary points. So I do want to emphasize that the next part, so step 3 onwards, it looks like any other type of calculus problem. And I'm referring to when you're finding stationary points and determining their nature. So you're going to, if you're looking or if you're trying to maximize a certain quantity, it's the same thing as finding a maximum turning point. So how do you find a maximum turning point? Well, you need to first find the derivative, let it equal to 0, and then find the stationary points. And then once you do find the stationary points, you need to test its nature. Is it a min or is it a max? So you use either the second derivative or you can use the table method. If you're not too comfortable with finding the stationary points and determining the nature, I highly recommend you watch the video I have over here, which talks about the stationary points and how to determine its nature. And the last step is to answer the question in words. So for example, if you wanted to find what is the maximum volume, then you can say x equals to 3. Whatever stationary point you get, it gives the max volume. Or sometimes the question is asked you to find the maximum volume. So you say the maximum volume is 15 meters cubed, something like that. Okay, so now let's go straight into the question. Example 1, the equation for the annual operating cost C in units of $10,000 of running a small factory is given by the following. So here's our equation where X represents the number in hundreds of units produced each year. So if I wanted to figure out what was the cost of creating 200 items or units or whatever the thing I'm producing, X is already in hundreds, so I just need to substitute X equals to 2 into here, and that's going to spit out the cost of producing those items. Part A, find the operating cost if no units are produced. So that means we're going to let X equal to 0. So we're going to substitute X equals to 0 into our cost function. So we get C equals to 0 minus 0 plus 20, or C equals to 20. Now C is not $20. If you look at the question, it says that C is in units of 10,000. So that means this is going to be an extra 4 zeros added on. So $200,000 even if you produce 0 items. So why do you think it costs money even if you're making nothing? Well, there's all sorts of costs involved. You can have cost of rent, cost of the machinery, cost of the different employees that you will employ to do other tasks other than creating the items. B, determine the number of units that should be produced to minimize the operating cost. Okay, so let's look at these words here. We're trying to find the number of units, which is X, that should be produced to minimize. So that's the thing that's the thing we're optimizing, is we're minimizing the operating cost. So we're finding the minimum for the constant. We're finding the minimum for the function C. So I want you to, for this next step, go through the process of figuring out what is the minimum turning point to this function. So we have C is equal to x squared minus 8x plus 20. Well, the first step in finding a minimum turning point is to find the stationary point. So let's find the derivative, C dash. We're going to get 2x minus 8. And then we're going to let C dash equal to 0. We get 2x minus 8 equals to 0, 2x equals to 8, or x equals to 4. Now, once you get this answer, this is not going to be your minimum. All it is, it's your stationary point. So you need to determine which one of it. Is it a min or is it a max? So your next step is, let's find the second derivative. So the second derivative is given by differentiating that, which is just a constant 2, which is going to be positive, which is concave up. So therefore, we can say x equals to 4. Refrain from writing is a minimum turning point because it's a new context. The context now is referring to cost. So I'm going to say gives the minimum cost. Perfect. And now part C says calculate the minimum operating cost of the factory. Now this here is not the minimum operating cost. It's how many items we need to produce in order to minimize this cost. So if you want to figure out what the cost is, all you need to do is substitute that x value into your cost function. So you get C is equal to 4 squared minus 8 times 4 plus 20. And that gives you 4. But remember that it's in units of 10,000, so that's going to be 40,000. Lovely, and that's it. Now I also want to mention that you have all sorts of different types of optimization problems. The more different types of problems you do, the better prepared you will be for the exam, because you have no idea which one they're going to put in the exam. You could get all sorts of problems on area, volume, surface area, time, distance, cost, but the more you do of them, their exam is only going to go through one of them. So the more of them that you do, the more better prepared you'll be. So now let's look at example 2. This one here is like a bread and butter optimization problem. So a farmer wants to construct a rectangular enclosure with an area of 5,000 meters squared. So this here is a fixed area. To reduce fencing expenses, they want the enclosure to have the smallest possible perimeter. So it looks like we're minimizing the perimeter. You see, that's my first step, is to figure out what is the quantity and am I minimizing it or am I maximizing it? Next, it says prove that the perimeter can be expressed as the following equation. So the good thing is they've given us a thing to work towards, but this is actually the hardest part of any optimization question, is figuring out how do you create that equation. The calculus part is the same for every single question, but this part here, you got to draw on different knowledge from all different areas in math. So since we're talking about area and perimeter, I'm going to put my little geometry hat on, my little measurement hat on, and I'm going to first of all draw out a little rectangular enclosure. We know that the area is fixed to become 5,000 meters squared. Now, just to help you understand like what the purpose of optimization is we know that this area is fixed at this amount. There are all sorts of scenarios that can give me an area of 5,000. Let me give you some cases. So let's say we have this length is 50. No, let's say this length is 50 and this here is 100. This is one scenario where the area is going to be 5,000 meters squared. Let me give you another scenario. Okay, now this is not to scale, but it's a crazy scenario where you have, this is a length of 500, or actually let me do 5,000, and this has a width of 1. This area is also 5,000 meters squared. And I can go on and on and on, and there's all sorts of options. I'll give you another option. Okay, now I can go on and on and on. There's so many different ways, but what we're trying to do is we're trying to figure out how should this rectangle be drawn, or what are the dimensions of the rectangle such that it has the smallest possible perimeter. Because if I were to add up the perimeters of each of these, the perimeter of this one is going to be 2 lots of 100 plus 2 lots of 50, which is going to be 300. But if I want the perimeter of this one here, this one's crazy. It's going to be 2 lots of 5,000, which is 10,000, plus 2 lots of 1, that's going to be 10,002. So you can see here that just because you have the same area, it doesn't mean you have the same perimeter. But our job is to figure out what is the smallest perimeter that you can actually choose if we have that fixed area of 5,000 meters squared. Okay, good. So it's hopefully you have a better understanding of what we're trying to achieve. So the next steps will be a bit more intuitive. All right, so now I'm going to continue drawing this diagram. I'm going to label my different dimensions. I'm going to call my length X and my width Y. Now let's start off with like the most simple way to represent the perimeter, because remember we're minimizing the perimeter, so we have to start from there. Well, the perimeter can be represented as 2x plus 2y. Awesome. But you can see here that this is not ideal. The reason why is if I go above to the steps, if you look here at the step-by-step guide, the step number 2 says create the function you need to optimize in terms of one variable. We're basically this scenario where you have x and y, but you only want it to all be in terms of just x or just y. So we need to get rid of one of these. I like to keep it in terms of x. I just feel nicer with x, but also they do tell you to keep it in terms of x. So the way you're going to do that is you need to use some other information they've given you in the problem, hint, hint, that the area is 5,000, to construct another formula. So area is 5,000. To construct another formula using these x and y values. So in this case, x times y equals to 5,000. And then you want to rearrange this formula and you want to make y the subject. Okay, the reason why you want to make y the subject is now you're writing y in terms of x, which means you can substitute that into here. So now if I sub that in, we get the p perimeter is 2x plus 2 times 5,000 over x, or the perimeter is 2x plus 10,000 over x. And that now is identical. That is now identical to the thing we were required to show. Now that's step number 1. Part B now says determine the dimensions of the rectangle that will result in the minimum perimeter rounding to 1 decimal place. So that means we're trying to look for the minimum turning point from this perimeter equation. And then now the steps should be the same. They should all be coming back to you. So first step is to find any minimum. You need to find the stationary point. So we're going to differentiate this. If I differentiate this, let's first write it in the form that is differentiable by bringing the x up. So we get 2x plus 10,000 x to the power of negative 1. And then now p dash is going to be 2 minus 10,000 x to the power of negative 2. Now I'm just going to bring that x squared back. Now to continue finding the stationary point, I'm going to let that equal to 0. So we get 2 minus 10,000 all over x squared equals to 0. Let's bring that fraction over to make it positive. So we get 2 equals to 10,000 over x squared. 2x squared equals to 10,000, or x squared equals to 500. So therefore, x is going to be equal to the square root of 500, which is going to simplify to x equals to 10 root 5. Okay, great. That is your stationary point. But we want to find the minimum turning point. So now you want to find the second derivative. So if I differentiate my first derivative, I'm going to differentiate this form. The 2 is going to go away. Now the negative 2 is going to multiply to the constant out front. It's going to give me positive 20,000, x to the power of 3, to the power of negative 3, which I bring down. And then now I'm going to plug in our stationary point of 10 root 5. And if I cube that on the denominator, we get 20,000. We get around 1.8. Now I'm not too fussed about the number. I'm fussed about the sign. So that's greater than 0, which is concave up, which therefore means that x equals to 10 root 5. Don't write is a minimum turning point because context, it gives you the minimum perimeter. Okay, now always read the question. Make sure you answer the question properly. Part B says determine the dimensions of the rectangle that give the minimum perimeter. Dimensions means length and width. We just have the length, which is 10 root 5. If I want the width, I need to find the y value, and I'm going to use this formula from part A where I made y the subject, which is 5,000 over x. So we're going to get y equals to 5,000 over x, which is 10 root 5, which gives you 500 over root 5, which you can rationalize by timesing top and bottom by root 5. 500 divided by 5 is 100, so we get 100 root 5. Okay, great. So that's going to be the y value, or the width, and then this here is going to be the length. So therefore the dimensions would be 10 root 5 meters by 100 root 5 meters. And now the next step, C, says calculate the total cost of fencing the enclosure if the fencing costs $52.30 per meter. So when we're talking about the fencing around this enclosure, we're referring to the perimeter. So what we're going to do is we're going to substitute the x value that gives the minimum perimeter into the perimeter formula over here. That is going to give us the minimum length. And then we're going to use the fact that the cost is $52.30 per meter, so we're going to multiply it there. So first, let's substitute x equals to 10 root 5 into p. P is equal to 2x, 10,000 over x. So we get p is equal to 2 times 10 root 5 plus 10,000 over 10 root 5. That's going to give us 491.9 meters. And then now if I want the cost of fencing, I'm just going to take that exact value on my calculator and times it by 52.30. Perfection. And that is going to be the total cost. Hurrah. Okay, next type of question you can get. Example 3. A box is created from a 60 centimeter by 40 centimeter piece of cardboard by cutting out 4 identical squares with side lengths of x centimeters from each corner. The edges are then folded up to form an open top box. Show that the volume of the box can be expressed as the following equation. Okay, so first thing you should always do if you're given a measurement or geometry problem is draw out a diagram. So we have a box here that is by, so let's draw out a rectangle. Okay, so I have a rectangle which is 60 centimeters by 40 centimeters. And this piece of cardboard is going to be shaped into a box by cutting out 4 identical squares with side lengths of x from each corner. So I'm going to draw in. So this dotted bit is where I'm going to cut it. Each of these are going to be side lengths of x. Okay, beautiful. And then what happens is once you chop off each of these corners, you're going to be able to fold each side, which allows you to then have a box. Can you kind of imagine that? So if I draw in the 3D version now, once it's been converted into a box. So this here is once I've chopped off all these sides. I folded up the sides afterwards. You get this 3D image. All right. So our job is to show that the volume of the box of this bottom diagram over here can be expressed as that. So if I want to find the volume of any shape, you're just going to, and especially rectangular prism, you just multiply each dimension, length, width, and height. Sorry, length, width, height. All right, so I need to figure out what these dimensions are by using this over here. Now, what else I'm going to do is I'm going to draw in. So over here, I'm going to have, I just redrew it because I was really not happy with how I drew it before. So this here is going to be the bottom of the box, and these here are going to be the sides of the box. So I'm going to figure out what's this dimension over here, given that each of these have a length of x. Well, you can see that this is going to be given by taking this whole thing, which is 60, and then minus 2 lots of x. And then this portion here is going to be this whole thing minus 2 lots of x again. Okay, and that is also going to be the base of this box. So I'm going to make it smaller. So this is going to be 60 minus 2x, and this here is going to be 40 minus 2x. Now, what's going to be the height of this prism? Well, imagine you fold this up. Do you see how it's just going to have a height of x? So this here is actually going to be x. Perfect. And now that each of these dimensions are labeled, I can go ahead and find the volume. So the volume is going to be given by taking all of these dimensions and multiplying them together. Okay, so now we're just going to expand it. I'm going to expand the first two. So we get 40x minus 2x squared. That's 60 minus 2x. And then now you're going to expand it further. We get 2,400x minus 80x squared minus 120x squared plus 4x cubed. And then now hopefully you realize that we can collect the like terms with the two terms. Let's bring the x cubed at the beginning. Collect those two, you get negative 200x squared and then positive 2,400x. Okay, you can see that matches up exactly with the question. Next, B. Calculate the maximum possible volume of the box. So now we're maximizing the volume. Now, good thing the volume formula is just right there. So let's continue. First step, we need to find the stationary point. So we're going to find the derivative, v dash. If I differentiate this, we get 12x squared minus 400x plus 2,400. Next, we're going to let v dash equal to 0. We get 12x squared minus 400x plus 2,400 equals to 0. It looks like we can divide this further. Let's divide everything by 4. So we get 3x squared minus 100x plus 600 equals to 0. Doesn't look like I can divide any further. You can either use factorization or you can use the quadratic formula. Okay, so after some deliberation, this is not factorizable, so I'm going to use the quadratic formula. So we're going to get x equals to minus b, so minus minus makes it a plus, plus or minus the square root of b squared minus 4ac all over 2a. Let's chuck it in. So our first solution is going to be 25.5, and the second solution is going to be 7.8. Both valid because they're both positive. But let's figure out which one of these two different options of our stationary points actually gives us the max. So now we're going to find the second derivative. So v double dash is going to be given by differentiating this again. We get 24x minus 400. If we sub in x is 25.5, we get 24 times 25.5 minus 400. We get 212. That's positive, which means it's concave up, which means it gives you the minimum. So therefore, x equals to 25.5 gives the min volume. But we're not interested in the minimum volume. We're interested in the maximum possible volume. So we don't really care about that. Let's check now. 7.8, hopefully it gives us the min. 24 times 7.8 minus 400. That gives us negative 212.8, which is less than 0, which gives us a maximum. So therefore, x equals to 7.8 meters gives the max volume. So that's going to be our answer. Always read the question before you conclude to make sure you're answering it. So the question says, calculate the max possible volume. This is not the max possible volume. This is the length of each of these squares such that it gives you the maximum. So that means you need to sub it back into the volume formula, the original volume formula, in order to find the max volume. So now we're going to substitute x equals to 7.8 into v. So we get v equals to 7.8 cubed minus 200 times 7.8 squared plus 2,400 times 7.8. And you do want to use the exact answer from the calculator, because if you just put in 7.8, you might get a rounding error, which will cost you a mark. This gives you 8,450.4 meters cubed. Beautiful. Now let's move on to the next question, example 4. Example 4, the formula for the surface area of a cylinder is given by S for surface area is 2 pi r plus h. If you don't know this formula, you can derive it very easily by expanding this out. So when you have a cylinder and you want its surface area, that is a bad cylinder, let me do it again. If you have a cylinder and you want to find its surface area, you're essentially adding up all the faces on it. So the two circles and then the rounded curved surface. So two circles, the area of two circles is simply 2 pi r squared. And then if you want this curved bit over here, the curved bit is actually just a rectangle. If I were to snip this down in the middle and flatten it, you just get a Coke can. Like if you snip it down the middle, like Coke can down the middle, and you flatten it, you just get a rectangle. So you can see the height of the rectangle, or this length here, is going to be the height, which is h. And then the length of the rectangle is actually going to be the circumference of the circle, which is 2 pi r. And you're given that r is the radius and the radius of its base, and h is the height. Show that if the cylinder has a volume of 60 pi meters cubed, so that is what is known, the surface area can be expressed as the following. So we have to create a formula for the surface area from scratch. And you can kind of get the hint that this is going to be the thing that we either minimize or maximize. So first things first is I'm going to draw a little diagram. So for my cylinder, we're going to have a radius of r and a height of h. So if I wanted the surface area formula, thank God they've given it to us in here, but you still need to know it for the exam. It's going to be 2 pi r squared plus 2 pi r h. Now, the issue with using this formula is it has two variables, r and h. So what we're going to have to do is we're going to have to get rid of one of them. Hopefully you see that we should get rid of h because we have more r's here. So it's going to be harder to change them all to h. It's easy just to get rid of one h. Okay, so we need to use some other info they've given us. And they've also given us that the cylinder has a volume of 60 pi. So on the side here, I'm going to use the fact that V equals to 60 pi. And I'm going to form an equation for the volume of the cylinder, which is given by pi r squared h. The area of the cross section, which is pi r squared, times the height. So we get 60 pi is equal to pi r squared h. And we want to make h the subject because we want to write h in terms of r. So then we just get h equals to 60 pi divided by pi r squared. The pi's cancel. So that means you just get h is equal to 60 over r squared. Okay, now we're going to sub that into over here and replace the h. So we get s equals to 2 pi r squared plus 2 pi r. And instead of h, we get 60 over r squared. Now, if we simplify this more, you can see one lot of r cancels top and bottom, but we still left with one at the top, which gives you 2 pi r squared plus 2 pi times 60, which is 120 pi all over r. And you can see that that is matching with the one in the problem. Yay. Next, B, calculate the minimum possible surface area. At this point, I want you to pause the video and have a go if you haven't already paused, and really try to follow the same steps we did in the previous question. Okay, I'm going to go through this now very quickly. So we're trying to find the minimum surface area. So we want to find the minimum turning point from this equation over here. So first, let me write this down. Now we're going to find its derivative. But before we do that, I'm going to rewrite this where r is at the top. Okay. Now let's go ahead and find the first derivative. That's 4 pi r. The negative 1 multiplies to the 120. We get negative 120 pi r to the power of negative 2. So s dash is 4 pi r minus 120 pi, and then r squared on the bottom. Great. Next, we want to find the stationary point. So we're going to let s dash equal to 0. We get 4 pi r minus 120 pi over r squared equals to 0. 120 pi over r squared equals to 4 pi r. I essentially move this over to this side to make it positive. That's actually a little bit confusing. Let me do it again. So I'm going to chuck this over to the other side to make it positive. So we get 4 pi r equals to 120 pi over r squared. Multiply that r squared over, we get 4 pi r cubed equals to 120 pi. And remember, we're trying to make the radius the subject, so I'm going to divide both sides by 4 pi over here. We end up with r cubed is equal to, the pi's cancel, and that becomes 30. So now if I take the cube root of r, we get the cube root of 30 is 3.1. And this is in meters. Beautiful. Now all that work, but we still haven't shown that it's a minimum. So let's go ahead and do that next. So to show that it's a minimum, we're going to find the second derivative, s double dash. So if I differentiate this, I'm going to use this form where it's an index form. So 4 pi r, the derivative is just 4 pi. The r goes away. We're just left with a constant. And then if you multiply the power of negative 2 down to the front, that becomes positive 240 pi r to the power of negative. Cool. And then now we're going to test whether this is a min or max. So if I plug in 3.11 into here, we get 4 pi plus 240 pi times 3.11 to the power of negative 3. We are going to get 37.7, which is greater than 0, which is a minimum. So therefore we can say r equals to 3.11 gives the min surface area. Okay, but are we done? No, read the question. It says calculate the minimum possible surface area. So it means we need to take this radius and plug it into our surface area formula, which I have written right over there. So we get s equals to 2 pi times r squared plus 120 pi over. So this is going to give you a surface area of 181.99. Let's just round it up to 182 meters squared for surface area. And then the last type of question we have here, this is probably the hardest one for today. If you can master this type of question, you are set. But it's a really good idea for you to expose yourself to as many different types of different problems as possible so that you're prepared for the exam. All right, so for example 5, a logistics company operates a truck from Melbourne to Adelaide covering a distance of 375 kilometers at a constant speed of v kilometers per hour. The cost per hour for a given speed v is 7,350 plus v squared cents. Show that the total cost of the journey in cents is given by the following. Okay, so let's really break down what they've given us. So it looks like the thing we're trying to optimize is going to be the total cost of the journey. And we're keeping into account that the distance from Melbourne to Adelaide is 375 kilometers and we travel at a constant speed of v kilometers per hour. We also know that the cost per hour for a given speed v is 7,350 plus v squared cents. So let's break down all this info. We know that the fixed distance between the two is 375 kilometers. We also know the speed is v kilometers per hour. And we know also the cost per hour. So 1 hour of traveling is going to cost 7,350 plus v squared, whatever the speed is. So the cost is proportional to the speed. If you travel quicker, the cost is more because you're using more fuel. Okay, so over here though, this cost equation for C is going to represent the total cost of the journey, however long the journey will take. So what I'm going to do first is it seems like the cost is going to be determined by how long it takes. So if I travel 2 hours or 3 hours or 15 hours, because this here is the cost for just 1 hour. If I travel 10 hours, then you need to take this whole thing and times it by 10. If it takes 15 hours, you take this cost and times by 15. but we're just going to generalize it and times it by some time t, and that time is how long it takes. So how do I find time? What formula can you bring up from year 8, year 9 that finds time? Well, it's the little Illuminati thing over here. Speed is distance over time. So according to this formula, time is going to be given by distance over speed. So the time taken to travel is distance over speed, where distance is 375 kilometers, that's fixed, and the speed is v. Okay, so now this here is the total time taken. So if I want the total cost of the journey, C, that's going to be given by the cost for 1 hour multiplied by the total time. Yeah, multiplied by the total time. So that's 375 over V. And then now if I multiply these guys together, or actually, you know what? I just want this to match up with this. It looks really close. How do you get it to look identical? Well, you want the V's to be, well, you don't want this V outside, you want it inside. So I'm going to multiply each of these by 1 over V. So we're going to get 7,350 over V. And if I multiply this by 1 over V or divide it by V, it just becomes a singular V. And then I'm going to bring 375 to. Okay, so if I wanted to figure out what was the cost of the journey, if I travel 60 kilometers per hour, you plug 60 into here, and then that spits out. Lovely. Next, B, find the speed that minimizes the cost of the trip. So we're trying to find the speed V that minimizes the cost. So we want to find the minimum associated with this cost formula. You see, it's always the same step with the calculus bit. It's this portion here that really trips up students. So what I would do if I were you, if you are so fine with the calculus, like the next bit where you minimize or maximize, just keep practicing finding the formula. So first thing we want to do is we want to find the derivative of C. So I'm going to expand this to make it easier. So if I times these two numbers together, we get 2756250, that's a mouthful, over V plus 375V. And then I'm also going to bring this up so it's to the power of -1. Great, so now if I differentiate this, negative 2756250, V to the power of -2 plus 375. Okay, and then now I'm going to find the stationary point by letting C dash equal to 0. We get negative 2756250 over V squared plus 375 equals to 0. Let's chuck that fraction over to make it positive, times V squared over 3,750 V squared equals to that big thing. Divide it, you get V squared equals to 735, and if you square root that, you get V equals to 27 kilometers per hour. Oopsies, I made a boo-boo. So what I did is I just added a 0 over here. It should just be 375. So that's why it was small. So you see, do a little sense check, because if you only had to travel 27 kilometers, you'd literally get a fine from the police because they're like, excuse me, you're going way too slow, you're going to cause an accident. So that's how I knew I was wrong. So have that same sort of like mentality when approaching a problem. Don't be just satisfied with whatever answer the calculator spits out. So that should be 375. So instead, that's going to become the square root of 7,350, which if I square root that, that is so much better. That is 85.7 kilometers per hour. That is more feasible. Okay, now I want to find the minimum, the speed that minimizes it. So I'm going to find the second derivative. If I differentiate this again, oh dear, we're going to get negative of this times -2. We get 5512500 V to the power of -3. The 375 goes away. And then if I plug in my 85.7, we get 8.75, which is positive, which is indeed a minimum. Yay! So therefore we can say V equals to 85.7 kilometers per hour gives the minimum cost. Hallelujah. And now the last step is to calculate the minimum possible cost of the journey. So now we're just going to substitute that speed into the cost function. So we get C equals to 375 bracket 85 point, oh, sorry. 375 bracket 7,350 divided by 85.7 plus 85.7. And that is going to give you a cost of $64,299.11. That's a lot of money. All right, and that is it. If you've made it this far, I'm so happy for you and proud for you. You are going to be thanking yourself in the future because you have mastered all these different types of problems. And did you notice that the more you did it, the easier it got? All right, thank you so much, and I hope to see you guys in the next video. Bye.